So, well,
sorry to interrupt. How do I delete this? I tried to write, and apparently I'm able to write in black. So now the screen is spoiled.
Clear.
How do I clear?
I think I did it now.
Okay.
Yeah, now it's clear.
Okay, sorry for that. So don't teach children these tricks, okay?
Very good. So this somewhat informal talk. I'm just going to communicate this main idea and discuss a couple of applications to strongly interacting dark matter and inelastic dark matter. So basically, you can see my cursor, right? So basically, nuclear isomers is some freaks of nature. So they exist for long time. These are excited levels of nuclei. You naively, we'll discuss that in more detail, you approach it, they shouldn't live long, but they store energy. At some point, people even thought, can we just store huge amounts of energy and get them on demand using neutrons and so on? But that never worked. So it appears as such something that exists, but not being ever used for anything. So here we kind of consider a possibility of sort of a niche dark matter search. Okay, so if you have a dark matter, the main thing important for us. So if it's a 100 GeV or TeV particle, you can have a momentum transfer between the nucleus and the dark matter comparable to the inverse nuclear size. In that sense, all multiples can contribute unsuppressed, and that is actually removing the main reason of longevity for these isomers. So you can use that to highly accelerate the decay, and then either look for some accompanying particles that appear in this decay, or have another dark matter experiment nearby that would basically catch the dark matter that got accelerated. Okay, so this is the basic basic kind of premise of this work. Of course, if you have just a normal dark matter that is 100 GeV mass or a TeV mass that interacts with nuclei elastically without any suppression, basically the standard ways of probing it using, for example, a xenon suite of experiment is, of course, far more advantageous because you have the largest mass and the lowest backgrounds. So to begin with, I want to show you this following plot. This is basically a level structure, not all levels, but some lower lying levels of tantalum 180M. Okay, tantalum is a cheap, very heavy material, sort of metal, and it's it doesn't have many radioactive isotopes. 100 tantalum 180 is unstable in the ground state decays to either tungsten or hafnium due to the beta decay or electron capture. This is all very nice. And so the lifetime of the tantalum 180 is a normal kind of, how to say, weak decay lifetime of a few hours. However, there is a second excited level of tantalum 180 that exists for, well, forever, basically. And that there's been very, very prolonged studies of trying to detect this tantalum 9 minus decays without any success. So, and it's not that all that rare. It constitutes basically the fractional abundance is 10 to minus 4. Some nuclear physicists know it very well because it's one of these sort of things that shouldn't exist. It's odd nucleus from the point of view of the neutrons and protons. It exists in relatively large numbers here, and this is a very kind of unstable from the point of view of nuclear synthesis nucleus, so nobody really understands why it's in such large numbers to begin with. And so there's been a lot of theoretical and experimental studies of this nucleus. Okay, so maybe I'll try to write now. I'll maybe stop share, and I switch to my so switch to my other device, and then maybe I can write here if you can see it. No. Let's do this. All right. This is some other notes, so I'll add this. So I hope you can see my screen. Sorry. Right. So let's consider a standard nuclear decay as well, sort of a standard nuclear decay, where, for example, I have.
Sorry, Maxim, we cannot hear very well. There's some interference. I don't know if it's because you switched to another device.
Maybe because I. Well, it's. Do you hear me now?
No, it's better.
Okay, so
yeah, thanks.
Let's do this. So let's say we have some initial to final decay of the nucleus due to, say, an electric dipole transition. Well, let's say the momentum or the energy of the emitted gamma is on the order of, say, 100 keV, which is relevant for us, right, for the nuclear decay. Then the decay rate, if we consider an E1 decay, would be, well, the interaction comes from the electric field of a gamma interacting with the operator of the electric dipole inside this nucleus. And so if we just put in all the relevant things that we know from quantum mechanics, we're going to get basically the transition frequency cube times the square of the electric dipole for the decay rate. Well, great. So this gives us something like alpha, which is, of course, part of the D, and then the product of omega and some sort of average distance associated with this dipole squared times omega, right? So if I continue writing this, then I get 10 minus 2. Then the transition frequency is 100 kV. Let me just very you know, crudely take this R over here to be like, say, half a Fermi, in which case this is going to be 100 MeV factor squared times another 100 kV, right? So when I just continue this simple estimate, I will get to 10 minus 8 times, well, what is it, 10 to the 5, let's say, electron volts, and this gets me to 10 to minus 3 electron volts, which is, of course, 10 to the 12 hertz. So we get to the sort of typical lifetimes here, obviously at the level of very short picosecond type lifetimes for nuclei, and we all kind of understand that. Well, there is a very big assumption here, big assumption, and a small parameter. Big assumption is that E1 transition was allowed, or M1, we get similar results, etc. However, if you remember this plot that I have just showed you, there was basically a transition from N9 minus state to 1 plus, okay? So if you consider, for example, an operator that relates electromagnetic current, or let's say just charge times the velocity of a nucleon operator times basically a polarization of a photon, then there is, of course, an exponent here that belongs to the wave function of the photon, and typically we stop this expansion right there. I remind you, we're in a situation where the wavelength of the photon times the characteristic distance is way smaller than 1, so we can always expand this exponent, right? So for E1 we take only the first order expansion, but for say 9 minus to 1 plus transition, we would need to take this, would have to expand it into a ridiculous power. So we would need to take additional hit in the amplitude, in the amplitude and the rate. So the rate of 9 minus to 1 plus will be like we had before, gamma of E1, but then it will additionally have this the omega times r, or this r nucleus over the lambda of emitted photon to the power 12 compared to this rate, right? 12. If you take 10 minus 3 and put it in the power 12, you get a ridiculously small number, and that's the reason why these freaks of nature live for so long. Very well. Now consider you have a different situation. Consider something that you have, and the same argument applies also applies to beta decays. There, of course, you have G Fermi, a small parameter to begin with, but you also have basically the additional well, ME is on the order of this delta E nuclear, so it's a small thing. So the very same arguments apply, right? So delta L large transitions are strongly inhibited. Now, if we consider, let's say we take some sort of a model where we have a TV scale dark matter, right? And let's say it scatters on the nucleus, right? Well, we know what to do then. Whatever it scatters with, we know that usually this is constrained by direct detection, etc. Now, consider now that what a momentum transfer could be here, even if the velocity of the incoming nucleus is very small. And small meaning not 10 minus 3 from the speed of light, but something like 10 minus 8 or smaller, which would then be really not all that constrained by direct detection, or because it will be a very, very slow nucleus. Now, if this part of the this slow dark matter would not impart any energy in the elastic collision with the nucleus. So now consider this to be a metastable nuclear state, right? And let's say star that carries this excess energy of 100 keV. Then the momentum transfer along this line, right, K, will be scaling as the square root of this delta E nuclear times the reduced mass. And I said, well, let's just say 100 GeV. Let's just say that we have the nuclear the WIMP, not a WIMP, but a mass of a dark matter commensurate with the mass of the with the heavy nucleus. So I put in 100 keV to 100 MeV, sorry, 100 GeV. That's the reduced mass, and from here we immediately conclude that the momentum transfer could be very large, on the order of 100 MeV. So this is a very simple argument, while showing that the energy exchange in this process is delta E stored in the nucleus, and the momentum transfer is 100 MeV. So of course this is comparable in size with the nuclear inverse nuclear radius, and therefore this 10 to the minus 3 over power 12 suppression is gone. Okay, and that's the basis for this application. So then our idea is to use this n star states to probe dark matter. And one example is this strongly interacting dark matter, dark matter that may be sort of already slowed down by the intervening material, and it moves very slowly in the lab, but it does have a potential for the metastable nucleus to recoil against and de-excite. And the second possibility is, of course, delta E can help accessing larger splittings in inelastic dark matter. Okay. All right. So I think I explained. Are there any questions? Okay. You can hear me, right?
Yes, we can hear you.
Very good. All right. So I'll then share my screen again, and I'll just walk you through some of these points again. This 9- state in tantalum lives long, and people actually, like I said, it's interesting state from the point of view of nuclear physics. They spend a lot of time trying to see how it decays. This is basically this argument that in the standard case, standard gamma beta decay, you have a large momentum transfer. I forgot to say, another possibility of having a large momentum transfer would be to, for example, scatter it on another heavy particle, on another nucleus, but the Coulomb suppression basically eliminates that process, so it doesn't happen with a large cube. So in the dark matter case, we have this suppression removed, and there's some examples of this plots. So that when you don't have this multiple expansion, you can still expand this exponent I showed into spherical functions, and the weights there will be spherical Bessel functions, and that's what's plotted here. So very simple thing that I was arguing, that the dark matter helps this nuclei to decay because it eliminates the strong multiple suppression, and the change for tantalum is from 9- to 1+, so it's quite significant. Now. Here are the examples of interesting candidates. For example, the possible metastable isotopes of different elements. And for me, really, the tantalum is the most looking most realistic because it's a harmless stuff. So you can find it, you can buy it off the shelf. It costs nothing. It doesn't pose a health hazard. But there are some interesting metastable guys who don't live as long as the lifetime of the universe. They live long enough, but they pose fairly significant health risks and so on. But for example, this state of hafnium has an excess energy of 2.4 MeV relative to the ground state, and that leaves 31 years. So if you are after the inelastic dark matter, then you may want to consider those because those have such a big overload of the energy. I just remind people that in an elastic dark matter, typical splittings that you can see through the or probe rather through the elastic scattering of nuclei are in the scales of 100 kV or so, and here it's much larger. All right, so tantalum is the most safe opportunity, and like I said, well, the strongly interacting dark matter is hard to hide if it's 100% of all dark matter, but it doesn't need to be. For example, exotic bound states of heavy stable colored dark matter particles with light QCD particles such as quarks and gluons may exist in small numbers relative to the total. And I refer here to recent papers by Reddy and Strume, whom I'm happy to see here, and others, Smirnov et al. Very nice papers showing that there should be some exotic abundance of heavyish states. Now, 10⁻⁵ is a very small abundance to be probed with, say, rockets floating. There are previous attempts to look for the strongly interacting dark matter over the range of. So you can't look for it using elastic scattering in the deep mines, but you can go up and try to probe it. Using set of balloons or rockets and so on, but then you have to see it over a huge background. So basically the idea, the interesting part here, of course, is that there is a density increase as we move towards, as this stuff sinks, first thing first, it slows down. It slows down to a thermal velocity, because it experiences frequent collisions with nuclei. But then at some point, the gravity gradually starts winning, and there is a terminal velocity for these particles, well known from the kinetic physics. Take Landau-Lifshitz series, volume 9 or 10. And you can find this formula there in terms of the elastic transport cross sections and so on. So because this V terminal is so much smaller than the initial velocities with which dark matter particles are coming into the atmosphere, which is 10⁻⁵. There is a huge enhancement in densities at deep locations. Right, because and so this enhancements are sort of plotted here, and for 100 GeV mass, and the sizable cross section, this enhancement can be, say, 8 or more orders of magnitude, 9 orders of magnitude, which facilitates a little bit of the reach. So here, with somewhat poor resolution, I quote. It's not seen, but you can access our paper to look at it in more detail. Anyways, let me see.
Sorry, Maxim, how much time you think you still
I think
need?
I'll take a couple of more minutes.
All right, that's great.
So I'm just going to say that this is if the abundance of dark matter is somewhere at the level of this strongly interacting dark matter is level of 10⁻⁵, using this metastable tantalum, one can basically probe this model by Michele and Alessandro. And similar things for the inelastic dark matter. So we contacted this group that was investigating the lifetime of tantalum in Kade's lab somewhere in Belgium, I think. At the depth of 300 meters, they were looking for these nuclear mechanisms for decaying from the excited states of 180 M tantalum through beta decay and electric capture down to tungsten and hafnium. So basically, if you look at this plot over here, if dark matter de-excites this 9121 plus, what you gotta look is, and the next step happens quickly, so you gotta look the de-excite, sometimes the transitions from 180 go to the excited states of hafnium or excited states of tungsten, and you gotta look for this 103.5 or 9.3.3 keV gammas. So this our colleagues who, of course, during their main sort of daytime occupation are doing the double neutrino-less beta decay, double beta decay searches, so they know how to do that stuff. So they've been looking for these extra peaks here in red at 103 and 93. At 93, there is unfortunately additional background from a known line, but not seeing this additional line at 103.5 already puts constraints on the dark matter induced lifetime of tantalum 180M to be that, and then we can kind of constrain. We can using our calculations for this traffic jam, sort of the build-up of the dark matter energy number densities, we can sort of start conquering these limits. The limits are not that strong because the abundance of tantalum in that state is 10 minus 4, so they add a few kilos. So this is in fact a gram worth and a few months worth of exposure, but already and a not optimized experiment with a rather small efficiency. So you can see that if you can do a dedicated search, you can cover quite a bit of parameter space, and this is for fractional dark matter abundance of 10 minus 4, which is already getting into a very interesting range for this example of strongly interacting dark matter that I just found, referred to. And then here the conclusions basically repeats what I have said. Sorry, it's not been a technical talk. It's a very sort of idea-oriented talk. So the next thing would be nice to do is to incorporate tantalum into shielding. It works well as a shielding. It's not a radioactive thing. Well, 180 M doesn't decay as I was trying to pass on this point. And when it's cheap, so if you incorporate it into the sort of a shielding of another sensitive dark matter detector, you have a strongly interacting particle that comes in, it de-excites on de-excites the tantalum, but it gets itself a kick of say 70 keV or a fraction of a 70 keV, and then now kinetic energy we're talking, and that can leave a significant fraction of that, say, in the xenon detector, and that could be sort of an interesting pet project to pursue for some of the dark matter guys if they ran out of things to do in the future. Okay, thank you.
Thank you very much, Maxim. So we proceed with questions now.
So if you had fast neutrons, would fast neutrons also cause the same transition, or?
That is correct. That is correct. So the fast neutrons being used to de-excite this nuclei, 180 M in particular. I think at some point people wanted to have this this as an on-demand storage of energy. So you have these nuclear isomers. Each of them contains a huge amount of energy, excess energy, right? You shine neutrons on it, and then you release a lot of energy on top. So, but it has to be neutrons with, say, tens of MeV transfer momentum, sort of, to this, right? So. It can't be thermal, I don't think.
So in this, I mean, when you give us these bounds and you convert to cross section,
yeah.
Okay, never mind.
Well,
is there an uncertainty there? I just wonder if maybe it's a stupid question. Probably not.
Well, go ahead.
I mean, so that cross section is the cross section for scattering on this whole tantalum 180M, or
that's
this?
That's the cross section for scattering on tantalum 180M. We estimated, well, there is this kinematic part, so to speak, that I was describing that due to this multiple expansion. But there is also a bona fide matrix element, which it's not measured, so we kind of borrowed it from existing literature, hoping that it's okay, but it can have an additional sort of order of magnitude uncertainty.
Mm-hmm. Okay.
All right, so other questions?
So I probably missed, but what is your estimate for the cross section? Just QCD, or?
Where you're talking about for there are two cross sections for strongly interacting thing. There enters two cross sections. There is there is more mundane sort of elastic cross section, and there is a de-excitation cross section. So we have taken what previous nuclear physics work to put in the value of the cross section. So the estimates go that on top of the natural, what's called the Weisskopf estimate, and on top of the suppressions associated with multiple expansion and whatnot, there are additional suppression related to the fact that one of the nuclei is in a deformed state, and so there are some K number conservation, which I'm a little vague on this. That enters as an additional hindrance factor on top of the Weisskopf estimate. So to be honest, it's an estimate, right? So is there an ab initio calculation ever to be done? That remains to be seen. And I can point you to the paper that we were using for the nuclear part of the matrix element. It's paper by the two authors from Japan, Ijiri and Shima, and that's what we were using, right?
Okay, thank you.
Right, so if there are no other questions, we can switch to